All right, so I'd like to welcome everyone to the 954th monthly meeting of the Amateur Telescope Makers of Boston. We'll have guest speakers, our own members. Our first speaker will be Christine Zacharer on amateur rocketry, and our second speaker will be Tom Consi on amateur radio astronomy. So next up, we've got the observing committee.
Very appropriate. Can you all hear me?
Yeah.
Yeah, this is from Julie. Julie keeps sending a lot of cartoons, and I don't know if Julie's on with us tonight, but I certainly thank her for reference. And this says it all. Stuff to get done today, straight away. Webb telescope images. You take a quick turn off the ramp there to go see that. So we're all been really enjoying those pictures. And by the way, Corey, don't feel bad about the difficulties you're going through now. I was a president for a full year, and I still couldn't figure out how to turn on the lights on and off at Phillips Auditorium. So you're doing great. Go to the next slide.
Thanks.
And our saying for this month: the feeling of being alone in the universe on a starlit night, cruising on wings of polished glass, flitting in seconds from a point millions of miles away to 1 billions of light years distance is euphoric. And that came from a man named Tom Lorenzen. And Tom is an amateur astronomer. He passed away in 2014, but he was and I don't know if you folks can see my image on your screens. I can't. Can you see me?
We can see you.
You can see me. Okay. I'm holding this up. I don't know how well you can see that, but this is Tom Lorenzen's book. It's 1,000 plus, the Amateur Astronomer's Field Guide to Deep Sky Observing. And this is a great piece of work. And he has a website, and I didn't put it down on here. I should have, but if those of you with paper and pen, or when you watch this on replay on the internet, if you go to his website called www.1000plus.com, you get Tom Lorenzen's website. And he was a Renaissance man. He had a lot of interest, and his webpage is just full of things from geology to artwork and the whole thing. So I really recommend you check out his website when you get a chance after this meeting. But very excellent book if you can get your hands on it. And by the way, I got my particular copy at the Conjunction. They have that little swap table area, and sometimes you can pick up a gem of an item there. So hopefully we'll be able to get the Conjunction going as well. We'll go to the next slide now. And I think this is where Rich picks up.
I will. Thanks, Glenn. I also have a copy of Tom Lorenzen's book. It really is valuable. Lots of great information in there. If you can find a copy of it, it's well recommended. And to go back to what was discussed at the quarterly board meeting, I've already purchased an Oxy 3 filter for the 25-inch, and tomorrow an 8mm ethos is arriving. The UHC filters are out of stock, and I bought a filter wheel that I've since returned, because when I looked at the measurements on the telescope, and if you do the calculations to where the focus drops below 2 inches to get it through the filter, it just wasn't going to work. So Corey, at some point in the near future, let's sit down and design a filter slide to incorporate into either replacing Dave Prouton's wooden riser box, or maybe attach it to there, but it has to be up near the focuser. There's no other place to put it. But anyway, so the telescope is working beautifully. I said earlier, you never have to put batteries in the tail rod again, because I hardwired that into the system. So when you go up to the clubhouse, when we have open, when the clubhouse is open, be sure to stop over at the 25-inch to take a look. Mid-month in July, I didn't write anything down about Comet K2. It's moving southward through Ophiuchus. You can find finder charts on most planetarium apps or on the web. It's about, I think, 7th magnitude, maybe 8th by now, closest to the Earth today. Or yesterday. So it's pretty close. It's visible in the evening sky in Ophiuchus, but Saturn rises at 10:50. In the evening, transits about 4 o'clock in the morning. The rings are tilted about 13 degrees towards Earth, with opposition occurring last night. Jupiter comes a little later at 12:30, 43 arc second diameter disk, with opposition coming on the 26th. And we'll go right down the parade. Neptune rises at 12:10, Uranus at 2:10, Mars comes up at 1:46. And Venus rises about 4:26. It's only 26 degrees west of the sun. Still a nice daytime object to check out. And since we're not going to have a meeting in August, I prepared a similar slide. Next, please, for the same things during August. with everything rising up a little earlier, as you would expect. Venus is a little closer to the sun. On the 27th of August, Mercury reaches greatest elongation east, 27 degrees from the sun. However, because as we approach the fall, the ecliptic to the west as the sun goes down makes a very shallow angle with respect to the horizon. And so even at its greatest elongation, the sunset at sunset will only have an altitude of 10 degrees. So if you're very brave, 27 degrees away from the sun is pretty easy peasy. Try to find that in the daytime if you want. And next, I think that's, and the Perseid meteor shower peaks on August 12th. And this, I'm predicting the view you'll have because the moon is full on the same night. So we might see some of the brighter meteors, but certainly not what the Old Farmer's Almanac would suggest you'd be able to see if you went outside to look at it. Of course, last night we had the super moon. It was all hyped up on the news. I suppose whatever gets people outside looking up is a good thing. I agree with Corey 100%. I think we should have more member events, whether they're at the clubhouse or out and about. And Glenn and I have talked a bit about that as we come out of, well, hopefully as we come out of COVID and move forward. So look forward to that sort of thing as well. Glenn, I think you're up now with the challenge of the
One quick
challenge,
point.
right?
I object to calling the moon super under any circumstances.
Well, and that's where I think the moon is super every night, of course, but but I know, Mario, I know. All right, go for it, Glenn.
Okay, well,
As you know, I'm a Mooney. No.
That's right.
okay, for July, it's the Turtle Nebula, NGC 6210. It's a planetary nebula in Hercules, magnitude 8.8, which makes it one of the brighter of the planetary nebulae. Size, it's about 20 by 13 arc seconds. And you can see its location there. It's just a little bit below the keystone of Hercules. And I found the best way to find it is by star hopping from Beta Hercules. And then the inset there, that magnitude, it's like, looks like a 2.8. I can't read that part of the next number, but anyways, about 4 degrees north and a little bit east of that particular star. And what you come to when you get to that area is a triangle of 7th magnitude, 7th and 8th magnitude objects, one of which at the crosshairs there, that is the planetary nebula itself. That's its location. We'll go to the next slide. We have some images. And again, we'll let the people who made these images speak. And this first one is the one by Mario Mata, and Mario I know is there, so we'll let him take over.
Yeah, disappointing actually. I did 3 the SHO filters, and it came overexposed. Did them again, it was still overexposed. Then I tried a third night, and it was so windy, it didn't come out well. So, not my best image. But it does look like a turtle, though.
Yeah, the part that makes up the turtle, actually, that's the part I mentioned, the 20 by 13 arc seconds. That's that bright central part. Mario's right. It's bright. It's going to be a hard thing to image. The outer part probably makes it in this nebula about twice as big, actually. The numbers that I gave are for the bright inner part. We'll go to the next slide now. And we have Doug Paul's image. And I think I saw Doug is there. So we'll let Doug get described.
Yeah, I'm here. This is.
You're very quiet, Doug.
Can you hear me?
Just barely.
Oh, okay. I'm having some computer problems, so we'll see what happens. This is 90 minutes with a 6-inch aperture. Some hints of the internal structure, and I suppose if you have a good imagination, you might be able to find a turtle in there somewhere.
It's green, isn't it?
Yes, it is in this image.
The turtles are green.
Yeah.
Works for
Very
me.
nice.
Okay, I guess we'll go to the next slide. And Chris, pick up on that one.
Yeah, similar experience to Mario. It's just such a bright object that you get the diffraction spikes from the spider, and it really removes some of the good detail you can get. I think this would be a great target for lucky imaging for anybody who's got a rig that's capable of that.
Speaking of diffraction spikes, I'm sure Doug is loving his 6-inch refractor. I think he's got a very large camera lens.
I used a refractor, which accounts for my lack of spikes.
By the way, while we're still on that picture, that's that triangle I was talking about, with your 3, 7th, and 8th magnitude objects. And the very bottom one there, the one at the very bottom over to the left, no, further down. And that's it right there. That's a double star. Now, an interesting thing about this is William Herschel discovers all of these things, it seems. If it's a non-Messier object and it's in the NGC, it was likely discovered by William Herschel, but he missed this object. And probably because of its small size. It was discovered by Friedrich Struve, who's that double star observer that cataloged the double stars in the mid 1820s. And he discovered that. And that star that we just pointed out the bottom there, that is a Struve. That's one of his double stars, and it's 2094. He discovered over 3,000 double stars, binary stars. And we looked at this and we tried to find it with a 25-inch. You're going to need some good seeing because it's magnitude 7.5 and 8. It appears as a single object in this image, but they're separated by about a little over an arc second. So that's a tough target, even for fairly large telescopes. And I think the night we tried at the clubhouse, there's just too much turbulence. You're going to need a really steady night. And I would say if you're ever looking at NGC 6210, think about that. If the seeing looks pretty good, you're getting good star images, just sneak down that triangle and see if you can see that double star, see if you can split it. It'd be kind of a neat sight. We just couldn't pick it out. And I've tried a couple of nights when the seeing wasn't good, and I just couldn't say I really definitely saw it. I thought I could see something when the sky steadied a little bit, just wasn't steady enough. And we'll go to the next one.
Glenn?
Yes.
If I could toss in one more thing, the surface brightness of that object was so bright that I had to use a quarter of my normal exposure to avoid overexposing it.
Right.
So it's very bright, but very small.
Again, at 9th magnitude, and because it's it is a bright object. Now, this is my sketch, and this is with the 10-inch reflecting telescope, 208 power, the field of view a little less than a degree. And really, I still couldn't see much detail there with that. I think you need to either be in a nice dark sky location or do imaging if you want to pick out the turtle part of it. And again, with that scope, I just wasn't able to split that double star, though I tried. Now we'll go to the next slide. And this is the August. This is the one that's coming up, 6772, another planetary nebula, but this is a whole different ballpark. This one is magnitude 12.7, and it's bigger. So you have a fainter object that's larger in size, so it's really faint. It's 70 by 56 arc seconds, which is approximately the size of M57, the Ring Nebula, but the Ring Nebula is several magnitudes brighter. So you're looking at something that's going to be very faint, and I did experience that. This one's located near Lambda Aquilae. That's that magnitude 3.4 star in the inset there. And it was about 3 degrees north and again, slightly east. And I think if Corey can just go a little drop, there's like a chain of stars right there. Yeah, I think Rich was talking about that. It was kind of like Kemble's Cascade, but this object is up there and it is faint. The first night, I couldn't really say that I saw it. This is with the 10-inch scope. The next time, it was definitely just, I had to use an O3 filter, and it was still visible only with averted vision. So it was a tough object to look for. I just want to preview, though, if you go back to Lambda Aquilae, our September, which I'm going to talk about in just a second, that September featured object, or the Observer's Challenge, is a brighter planetarium that's that's just located about a degree below Lambda Aquilae. So we'll talk about that in just a minute or two. Let's go to our images now. And we'll start with Mario. Go ahead, Mario.
Well, when you said the magic words, it's faint. Faint works great with my 32-inch. Bright doesn't work. I should have done like 3 and 5 second exposures. I would have done much better. Anyways, this one does show a fair amount of detail, and there's some outer material there. So I kind of like this one. This is a narrowband imaging, hydrogen, sulfur, and oxygen.
Well done, Mario. By the way, Mario brought up something that does remind me. I'm a very avid variable star observer. I'll be giving a talk at the Alcon convention in Albuquerque in a couple of weeks talking about variable stars. And my approach is going to be visual. And one of the big things in the variable stars now is, of course, the use of CCD work. And that really wiped out a lot of the visual work for a lot of us. But still, as Mario mentioned, when you get a bright variable star, it could really wash out a CCD image. So visual observers are still encouraged to look at some of the brighter variable stars and leave the faint stuff to the CCD folks. And then we'll go to the next one, which should be Doug Paul's image. And Doug, go ahead.
Yep, this one's 2 hours of exposure with the same rig. And I was able to use my usual 2-minute exposures. This is natural color. So I guess that's pretty much it.
Okay. We have an image from Chris, I think, coming up.
Yeah, from the middleman. Like Mario said, it's much easier on when you have a fast telescope and a big aperture. It makes it a lot easier to get these faint diffuse objects. It's still not a very big object, but it's easier. So this is sulfur, hydrogen, oxygen with the sulfur signal is pretty weak compared to the rest. But I believe this is 5-minute images, 12 each filter.
Beautiful, rich star field, at least for the camera on the big scope.
Yeah, the right one is just a crop, so it's same image. But yeah.
One thing I wanted to mention there, I know this will be tough, I know, for Corey, but if you point that pointer, put your pointer on in that wide field image there. Now just go a little bit to the right, it's a little bit the other direction. Oh, that's one. Yeah, that one. A little bit to the right, further down. And now a little, that one, no, go ahead, back up. That one right there. Now go back to the nebula. And then that first star that you were pointing at, up a little bit above there, that one. Now go a little bit to the lower left. There's another star. And then go further down like a triangle. That's it. I think you're going to get that star. You see those 4 stars. I point that out. Now, I don't know if this worked out, but I've got my sketch and I set it up so it would pretty much superimpose with that. So that's with the MAO observatory. The next one with Middleman, the next one is going to be what I saw with a 10-inch telescope, and it should be pretty much superimposed. Let's go to the next slide.
1 second before you switch slides. Chris, you took that picture?
Yeah, that was the
You got some
middleman.
you got dark lanes in the stars. I'm wondering if
Oh,
that's
yeah.
real or if that's, I mean, I'm wondering if that's dark gas versus just chance, but it looks like dark gas.
I
didn't
believe
read
I
anything on
believe it
that.
is dark. Those are real dark lanes.
Nice.
The errors and the flats don't look like that at all. So
Yeah, great.
Yeah.
That looks great.
Okay, and I noticed what Corey did was corrected the slide. I had it slanted over and I knew that would be a problem, but you can see those same 3 stars. The nebula is a little bit over to the side there. And so everything with my 10-inch was a dark lane because the only thing I could see was just a handful of stars. It is a pretty rich Milky Way field, but this is with a 10-inch telescope and it was tough. It was literally, I just had to, I probably spent 10 minutes just looking to make sure I'd seen this thing, and I positioned it relative to those stars. That's why it matches with what Chris had in his image. So I know I picked it up, but that's a challenge if you're an observer. It's a very tough target. You see the stars again, and then we'll go to my sketch, which is minus about 10,000 stars. And at least I picked a couple there. Those are probably 12th magnitude stars. So you can see it's a very faint object. And now a preview for September. And September challenge is another planetary nebula. This one's a little bit south of Lambda, and it's fainter. I think I've got the magnitudes here. It's magnitude 11.9, which is still faint. It's still, though, a magnitude brighter than the one we just talked about, and it's more concentrated. I have not had a chance to look at this yet because of Mario's friend, the moon. I'm waiting for the moon to get out of the way, and I'm going to give this one a shot, but it's called the Glowing Eye Nebula. You can see why in that picture right there. So that's our challenge for September, and you'll hear more about that when we get the newsletter back online and everything. In the meantime, I wish everybody a safe and happy summer, and keep looking up.
Thank you, Glenn.
Before we drop off the observers report, 2 things. Saturn reaches opposition on August 14th, not July 14th, my bad. And then on the way to this little planetary here, which really demands a filter. A shout out to Joe Henry. The carbon star V Aquila is right along the way here. So if you're in the area, do stop by and see that nice carbon star. It's very pretty.
Yeah, thanks for
Okay.
bringing that up, Rich. And by the way, that's true. And I made a finder chart for NGC 6751 and Lambda, NGC 6751 and V Aquily are all in that same chart. So there's going to be a kind of a special when we get to that in September. Thank you
Yeah,
for mentioning that, Rich.
That's a pretty start. Check it out.
Definitely keep it in mind. So first up, we've got Christine Zacharer presenting an overview of amateur rocketry. So Christine is a science and math teacher at Bromfield School in Harvard, Massachusetts. She is also the advisor to the school's GSA and advisor to its Rocket Science Club. In her spare time, she enjoys stargazing through her binocular telescopes and designing gadgets for 3D printing. Christine's talk will provide an overview on various aspects of amateur rocketry, from the low-power model rocket kits that we've all played around with, to the massive high-powered rockets, which require licensing and regulations. So a very exciting talk. Let's see. I'm going to,
Can you make me a co-host so I can share my screen?
oh, sorry, I thought I had.
Oh, you may
I
have.
may not have. I'm pretty new to this.
It's there, yeah.
Did that?
Yes.
It looks like it works.
Alrighty, okay.
Hopefully it's more smooth than mine. Yeah, sorry about that.
All right, so thank you, everyone. I'm not going to say this is not intimidating, because it is, because I know some of you are fairly expert and some of the principles of rocket flight and stability, which and propulsion and the physics behind it. I'm not really going to talk about that. It's more on the fun aspect of the hobby of model rocketry, and it's not unlike amateur astronomy, where where a lot of us are tinkerers and a lot of us are interested in the subject matter. Some of us do delve into the research, but some of us just enjoy the camaraderie of the hobby and the beauty of it and the fun of it. So that's kind of what I'm going to focus on tonight. I am going to be talking about amateur rocketry, and most people are familiar with our model rockets, Estes rockets that we may have built as a kid. But by way of background, I am a member of NAR, which is the National Association of Rocketry. I am a level 2 certified, federally licensed high-powered rocket flyer. I'm also one of about 22 educator mentors in the country, NART cert. So I mentor other educators who are looking to teach rocket science to middle and high school students. I am also a TARC mentor. That's Team America Rocketry Challenge, which is high school groups that get together and try and fly rockets within certain very narrowly defined parameters. And it's quite fun. It's an annual competition. It goes all year. It ultimately ends up in an international competition, but at least for our kids, it's the national goal involves scholarships and travel, and it's just a lot of fun for them. And then lastly, I'm also a member of the EEE Rocketry Association, TRA. I'm also level 2 certified there. EEE is more known for their experimental and high-powered rocketry. All right, so just a little overview of the National Association of Rocketry. It's the biggest international rocket organization. They concentrate mainly on model rocketry, low and mid-power rocketry. They also certify high-powered rockets. They certify high-powered rocket motors. They test them. There's many clubs, several of which I belong to. One of the oldest in the country is local to Massachusetts. It's the Central Mass Space Modeling Society, CMAS. There's MMMSC, the Maine Math and Missile Science Club, which is based out of Berwick, Maine. And then lastly, T-BARS, which is my club. It's the Bromfield Aerospace and Rocket Science Club. And that's limited to our school and staff only. NAR also publishes safety codes for the sport. Model rocketry is a very safe, it's a very fun activity. We encourage young kids and families to get out there just like we do with astronomy, and anything to get people out there to learn about the aspects of this hobby and the aspects of, beginning kinematics and science of propulsion is a good thing. Plus the kids just love it. Again, NAR does motor certifications. They do the TARC contests and they do USA flying contests. And kind of like golf clubs and whatnot, they have the licensing reciprocity with Tripoli Rocketry Association and the Canadian Association of Rocketry. So that's the NAR. Tripoli focuses mainly on high-powered rocketry. They're a West Coast-based association where there's big open spaces, no trees, and also EX, and that's experimental. EX is typically defined as class 3 rockets, and I will explain what those are in a little bit. It is a global organization, so anyone doing extreme high-powered and very large high-powered type of projects generally is going to belong to Tripoli. Also, if you're flying non-commercial motors, if you're flying home-built motors, you can only do that at a Tripoli event and be legal. And I'll explain why you're being legal. They don't necessarily have clubs. They have what they call regional prefectures. And again, most of them are based out west. I do not believe there's one in New England. There is one in New York, and there's one further south in the Delaware, Maryland area. They are also the keeper of the official records for flight records for altitude, velocity, impulse classes, and all sorts of records that go on in the model rocketry hobby. Also, TRA's big claim to fame was the 2002 federal lawsuit against the Bureau of Alcohol, Tobacco, and Firearms after the ATF classified APCP, which is ammonium perchlorate, as an explosive under 18 USC, I think 127 or something like that. But the ATF classified the main propellant that is used in high-powered rocketry as an explosive after 9/11. It basically killed the hobby. The Tripoli Rocketry Association sued the ATF and they won. And APCP was classified as a non-explosive, which allows, amateurs such as myself to possess quantities of it. These are just some of the, scores of high-powered rockets that I have here at home. And store safely otherwise. But, APCP is relatively safe to store. So I'm going to be talking about model rockets versus mid-power rockets versus high-powered rockets versus experimental rockets, what they are, who flies them, what are the requirements, what are the licensing requirements, and what are some of the things that we do with them. So model rockets are generally low and mid power, and those are the ones that you may have played with your kids, or you may have played around with your kids, or with yourself when you were a kid. Typically, everyone is familiar with, the Estes rockets, the black powder paper roll motors with the clay nozzles in the bottom and the explosive charges on top that ejected the nose cone. This is in the background is a little rocket that I built. I go for the more Buck Rogers style of rocket. I actually built the 3D printed model of the same rocket. I have not flown this. I use this for demonstration purposes when I talk. But this little guy here is probably down in my garage somewhere. But the definition of a low or mid-powered rocket or a model rocket is it's lightweight. The materials it's built out of generally are lightweight. You can't use metal components. Or if you do use metal components, they have to be interior to the rocket and they have to be very limited. You can only fly certified, commercially available, unmodified motors, and they're generally black powder. Although recently, Aerotech has produced a series of APCP low and mid-powered motors. So those are available. The real definition, though, is that the rocket must be less than 1,500 grams in weight. And we say wet weight, and that means the total combined weight sitting on the launch pad with the fuel ready to go. So it has to weigh less than 1,500 grams. It can have no more than 125 grams of propellant or 320 Newton seconds of total impulse. And so that's important because it's an either or thing. And I'll explain that a little bit later, because some motors that are generally considered non-high power become high power because they exceed one of those two parameters. Again, we're used to the designation on the Estes motors. This is an E12-4 motor, which means it's an impulse class E. The 12 indicates its average impulse, and then the 4 is the delay before the explosive charge goes off after motor burnout. So they have tiny little motors from quarter A's all the way up to D's in black powder. The space you're supposed to maintain away from a launch is 15 feet. That's pretty close, as you can see from the folks here in the background for this little rocket taking off. And then E, F, and G motors, which are also considered mid-power motors. The space that you're supposed to maintain from a launch of those to maintain safe is twice that, or 30 feet. Some F motors and some G motors are high powered. So these rules do not apply to those particular high powered motors. So this, I'm not going to go through all of this, but the whole idea behind the impulse classes A, B, C, D, E, F, and G is the impulse, the average impulse of, or the total impulse of the motor doubles with each letter grade. So in A motor is the lowest impulse class. It goes up to 2.5 Newton seconds. It's not very powerful, but we go all the way up to a G impulse motor, which is 160 Newton seconds. That's 16 kilograms, which is about 32 pounds of average thrust, 32 pound-seconds of average thrust. So, you know, a little tiny G motor, you know, one of these, you know, could pick up your cat, so to speak. It provides enough thrust to pick up a small dog or a small cat. Okay, it's kind of fun to think of it in that scope. I'm going to show you this little rocket in a second. I have it right here. This is a rocket. I built it as a proof of concept rocket. It's entirely 3D printed, including the motor retention system. The proof of concept was the rocket is made. If any of you 3D print, it can be printed with a single roll, a single 1 kilogram roll of PETG filament. It weighs less than a kilogram. So obviously, and so 2.2 pounds, so it could be a low powered motor. But it's fully dual deployed. And what I mean by that is it's got some really cool things. It has a flight computer on board, It has a backup flight computer on board, as well as downlinked GPS and flight event telemetry. So it's kind of a really cool rocket, and it certainly doesn't need to fly with all of that, but it can. And you know, that it's just a fun little proof of concept that I did. It can fly low power, and it can also fly high power. Oops, let me go back. Oh, no. All right, and so this was its first flight. And what's kind of interesting about this is this was several years ago. And as far as we know, this was the first high-powered 3D rocket ever built and successfully flown. And that's the kind of cool thing about this.
Christine Zacharer has I wanted to be a Saturn V, so mom made me this costume. Launching on an Airtex G80. It's going to deploy a main chute at 400 feet. It says entirely 3D printed. Launching in 5, 4, 3, 2, 1.
So not super impressive. And right up here, you heard a little pop, and that's its apogee event. And then the chutes are going to deploy right there at about 400 feet on its way down. And then it lands.
Perfect.
So 54-inch. And so, oh, why can't I go to the next screen? Here we go. So I'm going to, and I don't think that was the next screen. Yeah, okay. So I'm going to jump into high-powered rocketry now. And I kind of skipped over mid-power rocketry, but that's part of low-powered rocketry. It's just the FG and E motors are generally considered mid-power. They're larger, low power. But high-powered rocketry now we get into some serious serious forces, serious velocities, in serious physics. And it's always kind of humorous when we see some of the college teams that come out to fly and they ask for advice. I mentor the Tufts Rocketry Club, and we get the MIT club comes out to our launches. And it's fun to see the students come out because they don't want help, because they think they know everything, which is great. And they understand conceptually what F equals ma, and they know what a Newton is and whatnot. But when they apply it to real life, they don't really get it. And they don't understand the forces involved. So high-powered rocketry, the models are generally built out of composite, and metal construction is very typical. There's a lot of aluminum, there's a lot of steel, there's a lot of titanium, there's a lot of boron, there's a lot of carbon fiber, and there's a lot of fiberglass in high-powered rocketry. As a matter of fact, that's pretty much all it is. Again, only certified commercially unmodified motors are allowed in high-powered rocketry. There is no weight requirement, and I will get into some of the big heavyweights coming up a little bit later. The only weight requirement is that the rocket itself cannot exceed 1/3 of the average thrust of the motor. And so we know weight is given in newtons, okay? It's given in, we typically think of it in kilograms or pounds, but we have to think of it in force. Okay, and it's given in newtons. So a rocket that weighs, a rocket that has a mass of, for instance, 10 kilograms, right? We know has a weight of 98 newtons, right? And so our average thrust has to be 3 times that, and typically it's 5 times that. Because we want sufficient velocity by the time it hits the end of the launch rail, by the time it hits the end of the launch tower, to have dynamic pressure to give the rocket stability. I'm not going to be talking about the physics of that. And this is where the numbers really come in. And that's over here. a high-powered rocket can have no more than 40,900 and that's a typo, 960 Newton seconds of average thrust. To put that into something, you know, that some of us would understand here, that's 9,200 pound seconds of thrust. Okay, that's over 4 ton seconds of thrust. That would pick up a Tahoe. And it would put a Tahoe several thousand feet in the air, depending on what motor you're flying. So these are some of the high-powered rockets that we're flying. I'm going to show you 2 of them that my son has recently flown that were in this class. The distances away, this is a high-powered rocket I built back probably about 15 years or so ago. I no longer have it. It's on an island somewhere in Maine. That's what the GPS coordinates gave it, and I was never able to recover it. Unfortunately, this was not its last flight. It was one of its early flights. I just particularly like the picture, but the setback clearance from a high-powered rocket is from 100 to 2,000 feet. And for some of the bigger projects, even 2,000 feet of clearance, you can feel them. And you can feel your bones rattling and your ears hurt. They are so powerful going up. There are other requirements that has to, high-powered rockets have to comply with the NFPA Rule 1127. That's the National Fire Prevention Association rule. This rocket up on top is a rocket I'm building right now. But these indicate some of the classes. All H-class motors are high-powered, but some, like I said, some Gs and some F motors are also high-powered. So it's just to give you some idea here. And they go, high-powered motors for regulated, commercially available motors go all the way up to O impulse. And that's the 4,960 Newton seconds of impulse. And you can see they double each letter class. I am going to unplug here for a second, and hopefully I won't lose everybody. Oops. Can you still see me? Okay. So I'm going to move her. And so this is the rocket that was in that picture. I don't know if you can see it. It's this one here. It's the really big one. This rocket's almost 11 feet long. It'll be about 50 pounds on the launch pad. This is to give you an idea of the size of this. The rocket that it's sitting next to is a full-scale Arcus. And that's, those of you who are my age may remember NASA's early forays into atmospheric research. You used the Nike Smoke and the Arcus, which was the Atlantic Research Corporation's sounding rocket. And that's a full-scale version of that rocket. All right, and I lost my screen. There we go, okay. Oh, and there's the Crescent Nebula. That's a la Mario Mata, because I just like the way he interjects various AP photos in his presentations. So I thought I would do something similar. I stole that from you, Mario. So thank you for the inspiration. And I got the Bubble Nebula too, which is right over here, which is Planetary Nebula JU1, named after its amateur astronomer discoverer. All right, so for high-powered license certifications, there's level 1, which is you can fly anything up to an I impulse. Level 2, you can fly anything up to an L impulse. Level 3, you can fly anything up to an O. So if you're a level 3 certified, that means you can also fly a class 3 above, which means you can fly a P impulse or above in over 100,000 feet. All high-powered rockets require what we call an FAA waiver. If any of you are pilots, you know what a NOTAM is, and that's a notice. That's a notice to flyers. Our launch dates and locations. The FAA issues a NOTAM, which is a restricted airspace. And some of our line, we have altitude waivers where we can't fly over 10,000 feet, 15,000 feet, 35,000 feet, 50,000 feet. And if, according to the FAA, and flying over those waivers is considered a serious offense, you can lose your license, and you should lose your license. So this is my son, Thomas, and my rocket boy. So to give you an idea of the size and scope of a high-powered, an Estes motor and a high-powered motor, this is the fatter one that's not quite as tall as a 98 millimeter 6XL. And the one it's next to is a Loki Research. It's a special casing, and it's actually a lot of fun there, but there's one of these casings and 4 of these casings on the right. So there's one of the big ones and 4 of the smaller ones in this rocket to the right. And that's Tom in Utah in the Salt Flats. Some of you may recognize. And this is a 400-pound upscale Aerotech Sumo, which he flew, and I have a video of that coming up. So we'll be watching that. High powered by the numbers. The biggest commercial amateur motor is a CTI 025,000. It thrust at 3 tons for 1.3 seconds. So this is, kind of gives you an idea of some of the things that we fly. My son Tom has one, and we'll be flying one with a dart on top. It's a 2-stage rocket, and it's a project that he's doing with another individual. And they plan to fly this thing, at least the dart, the 2nd stage, to over 100,000 feet. So that's kind of cool. Velocities easily in excess of Mach 2. I've flown up to Mach 1.7 myself personally. My son has been over Mach 2 several times. G-forces in excess of 200 Gs. To put that into perspective, a paperclip would be difficult to pick up at 200 Gs. We have to be careful about wiring. We have to be careful about things that we put in our rocket and where they're situated when we hit those G-forces. We have apogees common in high-powered rocketry are 5 kilometers, often over 10 kilometers. The largest single amateur motor ever flown was an S-impulse, 500,000 Newton seconds of impulse. It's a pretty cool flight. Unfortunately, there's no YouTube video of it. It would be a fun one to watch. This is kind of a really fun video, and I don't want you to blink when you watch this.
4, 3, 2, 1.
So that rocket reached almost 15,000 feet. It was 230 Gs by the time it hit the end of the launch pad and had a maximum velocity of Mach 2.3. It was a tiny little rocket. It was a minimum diameter 38 millimeter rocket, so it's only about just under 1.5 inches in diameter. It weighed less than a pound, and it had a I-1299, which was basically the biggest I motor you can put in the smallest, tiniest little rocket you could. And it's this one right here. And it was just a fun little project. I've flown this rocket many times. I personally did not fly this. My son flew this at that time. It's just some of those fun little things that we do.
4, 3.
We already saw that. So again, my son Tom, and I've got to show you this because this was a world record. He just set this. Estes, everyone's heard of Estes. They have a competition every year to see who can fly the biggest motor in a stock Estes rocket. And so far, the of the 15 or so years that they've had this competition at LDRS, which is the biggest rocket show every year. This one was in, he's in Utah. He was going to fly it there. He actually did not fly it on this day. He flew it just a couple of weeks ago in California. The rocket is called the Big Daddy, and it's an Estes Big Daddy. It's actually this rocket here, although it's not actually this rocket, but it's a Estes kit rocket. And it's one of the bigger rockets that Estes makes. Up until this year, the largest motor ever flown in it was a jet. He put an L in it, thus the El Padre, so JKL. And it's actually the biggest L motor that's made. So no one could ever actually fly a bigger motor unless someone makes a bigger motor than what it is. He flew an L910 C-Star. C-Star stands for the APCP formulation, which is the exact same formulation that is in the Space Shuttle solid rocket boosters. Another Mario Mata special, and this is in Black Rock. This is how jealous we should be about dark skies. This is in Black Rock, Nevada, which is a national certified dark site. This was taken while the sun was still up during a dust storm, and there's a dust storm rainbow. And that's what my son was taking a picture of, and he shared it with me. And I'm like, you realize you can see Ursa Major in the background. And not only can you see Ursa Major in the background, but you can see Alcor and Mizar, the double star in his picture. And that's what's inset over here. And this was taken with an iPhone. And, you know, I'm just so jealous of the dark skies that he gets. So, I, for some reason, couldn't get the video to work. But I'm going to skip it. But in any event, he did fly the rocket. It's actually kind of fun. Here's the Sumo. This is also in Utah. It's just a beautiful picture. That's the rocket that you saw him preparing, the really big one. There's 5 motors in that. It's a central M motor central N motor surrounded by 4 L motors. This is Porthos. It's another one of his big projects that he's working on with another major rocket enthusiast. This is obviously a very large, over 400-pound amateur rocket. And so we're going to watch a little bit of slow-mo video of these 2 rockets going on. And I'll just skip ahead a little bit to Porthos. And there's Porthos. And this was taken through a telescope, obviously. And let me see, I have 2 of those in there. And I think there should be one more slide. And I think that's it. I thought I had one more slide. But that's it. If there's any questions, you know, I'd be more than happy to answer it. Obviously, I am not, and before anyone asks, I am not a fan of Elon Musk, so.
Christine, I have a quick question for you.
Sure.
They must cost a fortune to build those rockets.
Yeah, well, yes and no. So we do a lot of scratch built rockets from materials and so that certainly helps. And I did not explain about experimental, but yes, the motors, I mean, a launch for a high powered rocket could cost over $1,000 easily.
The cost of the motor, right?
Between the motor and all the expendables. So, you know, there's, in a typical high-powered launch, there's 4 explosive charges, there's explosive bolts, you know, there's all sorts of separation equipment, there's stuff that gets burnt up. Sometimes you lose, you know, you burn up a 10-foot parachute, you know, it happens. But yeah, an L motor can cost $300-400. So, and some of the larger ones, that the Sumo that has had almost $5,000 worth of propellant on board.
Wow.
And those were all homebrews.
And
Those were not commercial.
another quick question: when you're launching rockets with multiple motors, how do you ensure the ignition is simultaneous on all the motors?
Okay, so there's a couple of techniques that are done for low power. They usually do what they call a black powder flash pan, where they put a pan of black powder underneath the rocket, when they're doing clusters of motors, and they just ignite the flash pan, and that flashes up into the motors themselves and ignites them. For high powered motors, though, it's kind of interesting. I didn't bring any igniters down with me. I didn't bring any igniters down with me, but they use electric matches that are generally, we either build them ourselves with nitrile wire, or we add extra thermite to them, and they're rather large, actually, and they're pushed up into the core of the motor itself. And sometimes we also put motors. We ignite a small motor, and it's pointed up into the core of the larger motor, and we use those smaller motors to ignite the larger motors. So sometimes we do that. With multiple motors, they're oriented such that if you don't light them all, they're slightly tilted into the center of gravity. So if you don't light them all, they're not going to destabilize the rocket. Okay, so they're pushing into the center of gravity. With Porthos, the largest one you saw, you might have seen a spike right at the very end as it was leaving the screen. That was one of the outboard motors igniting about a half a second after all the other ones did. That's exactly what that was. So yeah, it can be a challenge sometimes to get a cluster to all ignite at the same time.
Christine, one more question. You just mentioned thermite.
Yeah.
What do you guys use thermite for?
For the igniters.
The igniters. I mean, that's a great reaction all by itself.
Yes.
That's a great reaction.
Yes, it is.
And these rockets that go up that high, I know they're loaded with electronics, but are you able to track them visually?
So the really big ones with optics, yeah, we usually can. I mean, the super heavy ones, if they go more than 10,000 feet, that's saying something. So they're generally pretty easily visible their entire way. But some of the smaller ones, the one I showed you that went, 15,000 feet, that was out of sight in just a matter of, in the blink of an eye. And, this little guy has flown, like I said, to 15,000 feet. You can't see it over 1,000 feet.
It's time following golf balls at the driving range.
Yeah. So there are, we do have radio trackers and GPS trackers on them. So.
Awesome. Looks like Tom has a question.
Thanks, Christine. This is super fun talk. You talked all about solid propellant rockets. Are there any liquid propellant?
Yes, absolutely. There's not only are there liquid, but they're hybrid rockets too. So yeah, some folks do fly liquid oxygen, nitrous oxide as the oxidizer, and hydrogen is the propellant. Liquid hydrogen is the propellant. It's quite the setup. There are commercial hybrid and liquid rockets. Aerotech is one of the big rocket motor manufacturers, and they do produce both hybrid and liquid motors.
Yeah,
so
really, really cool. And you didn't mention Robert Goddard, but
I did not.
He's a local Massachusetts guy, wasn't he?
He is a local Massachusetts guy. I did mention CMAS, and our club, the Central Mass Space Modeling Society, built the model that currently sits in the Smithsonian Institute of Robert Goddard's first liquid fueled rocket.
That's cool.
And it's a working model.
Did
And
you
it
test
has-
it?
Yes, it did fly, it works, and it is in the Smithsonian.
That's awesome. All the videos I see of the high power rocketry always seem to be flown in the desert or in the salt flats. What, where do they fly in the Northeast? I don't, for like medium
Yes.
powers and.
So we had a turf farm in southwestern Maine, in Berwick, Maine, which was ideal, but we lost that launch field during COVID. And we have not been able to, the owners have not allowed us back on the field. So now we fly in Western New York, in Potter, New York, and we fly in NDRA is one of the clubs I had mentioned, and they are in Maryland, and we do fly down there. So both launch fields are within 8 hours of here. So yeah, it's a lot of travel, but
A big event with
yeah, they are big events.
up to it.
They're like 3-4 day events. So, you know, you're not just going for a single day. I generally fly more little rockets where we can fly around here. We fly actually locally in Acton and in Amesbury. So.
Nice. Looks like Christian has a question.
Sure.
Thank you, Christine. That was so much fun. I'm curious, how much, can you speak a little to how much are you able to recover of these rockets depending on size? And secondly, can you do anything to control where they go and where they come down?
So we are able to do some control on the way up, but we cannot do directional control. That's actually for high-powered rocketry. For low-powered rocketry, we can pretty much do anything we want. But for high-powered rocketry, actually putting on directional controls is a federal crime. And I think for obvious reasons, because now it becomes a guided missile. And like I said, some of these rockets are essentially missiles. So guiding them on the way down, there are techniques to do that. They do have parachutes that are, square parachutes that can be guided on the way down. There are some commercially available ones, and people have also worked on ones. But I mean, the techniques that we use, it's a technique called dual deployment, where we release a drogue chute at very high altitude, so at apogee, and so the rocket comes down really quickly. It'll come down at several hundred feet per second. It's not coming down ballistically, it's coming down broken, but it's coming down very rapidly, so it's not getting carried away in upper atmosphere winds, which can be 100 miles an hour. And it's not until 400, 500, 1,000 feet where the main parachute is then deployed. And that will significantly slow down the rocket before it lands. But some of these bigger projects can land several miles downrange. And that's pretty typical.
Is the tube itself reusable, or do they just break up?
Oh gosh, no. They're totally reusable. That's the goal. Yeah, I mean, every once in a while we do have an incident called a CATO, a catastrophic event, where we call them cool launches and really cool launches, and the really cool launches are generally not good for the rocket owners, but everyone else enjoys it. So but I mean, to give you some idea, this is the nozzle retainer for the project, my big project that I'm building right now. And this is just the diameter of the nozzle, which is basically a 100 millimeter refractor. So it's a 4-inch nozzle. And it's 20 kilograms of propellant. So
awesome.
Yeah, it's fun.
Is the telemetry and tracking radio commercial or amateur?
Both. So in the old days, we used to use the falconry, the radio transmitters that was used in falconry. And because they were very long range, and, even though they were dumb as far as distance, there was signal strength that you could use, but you could use a Yagi directional antenna and, figure out the direction that you're going in. You could triangulate on it the signal pretty easily. To give you some idea, this was about, 10 or 11 years ago. It was, believed, down in Maryland. We planted a rocket. It came down ballistically, and it had a falconry radio transmitter in it. The rocket was demolished. We dug it out of the ground. We were still able to get a signal from the transmitter underground from 2.5 miles away. So that was, that the equipment that we're using, that was a home built unit that we made. Unfortunately, we don't have it anymore. We lent it out to someone and we never got it back. So, yeah, there are commercial devices too, but it's a little bit more fun to make your own.
That was really fun. That was very cool. Something I've always sort of observed from afar. I see posts and stuff of people launching. Always looks like a blast. So, thank you, Christine. Any other last questions before we move to Tom's talk? All right. Thank you so much. Okay. Let's hopefully this shares the first time. So thank you, Christine, for your talk. Oh, okay, it did work. So next up we have Tom Consi, Exploring the Universe in the Frequency Domain. So Tom is a teaching professor in the Department of Electrical and Computer Engineering at Northeastern University. An ATMoB member since 2016, Tom's astronomical interests include planetary imaging, spectroscopy, and radio astronomy. Tom will discuss his first foray into amateur radio astronomy with the goal of detecting the neutral hydrogen or H1 signal from the Milky Way. He'll present the design of his simple radio telescope consisting of a 1 meter parabolic mesh antenna and a software-defined radio, or SDR, and open source software. I saw Tom on earlier. Oh, there he is.
I'm still here, so I need to get control of the screen.
So I've made you a co-host, so the share screen button at the bottom should be green. I think you can, should have the ability to.
Okay, so let's see.
I see your screen.
All right, let me put it in. All right. So you don't see that, you do see this? Do you see the slide, or do you see sort of
the big full screen slide?
You see the big full screen?
Correct.
Oh, okay, good. Then it's working fine.
Awesome.
All right. So, okay, well, thank you for that talk, Christine. I think just about everybody in this club, I imagine, had started out building rockets as a kid, and then a lot of people revisited later in life. So the term "born again rocketeer" was happened, and I happen to be one of those too. But I'm going to switch gears a bit, and I've always been sort of interested in the possibility of building a radio telescope and seeing what there is to see, in big quotes. And I decided to do it, basically because I started teaching myself about these devices called software-defined radios. And it turns out they're sort of revolutionizing amateur radio astronomy as well. So I'll also give a little sort of introduction to those things. It's nice that the latest issue of Sky and Telescope had a radio astronomy article called Mysterious Radio Signals. And there was a nice quote there. It says, while the sky appears largely unchanging to our human eyes, it puts on a spectacular display of fireworks every day that's detectable with the eyes of a radio telescope. And that's by Shivani Bandari from the Netherlands Institute of Astronomy. And that may be the case, but when you talk about eyes, this also shows one of the difficulties in trying to sort of, especially if you're starting from zero, as I essentially did, to get into this. Because if you have even a lousy telescope, you can see, say, something in the sky, say Jupiter, you could point the telescope at Jupiter, and even though the image might be distorted, you can definitely see it. So you know your system is receiving the signal, okay? But we don't have sensors for radio frequency or microwaves. So when you're starting out, it can be very frustrating because you're getting all kinds of strange signals and you're not sure exactly what it is you're seeing. Fortunately, there's a big online community and plenty of people are willing to help. So with that and a lot of experimentation, you manage to sort of get things going, as I have in the last few months. So what I decided to go for my first foray, there's a lot of different things you can look at in the RF, but I decided to go for the neutral hydrogen signal. Let's see, high E controls there. Okay. So the neutral hydrogen, well, hydrogen has a proton and an electron. And of course, hydrogen is the most abundant element in the universe. When the proton and the neutron spin sort of in the same direction, they have parallel spin, the molecule is at a higher energy level, higher than what? Well, higher than if the electron is spinning opposite what the proton, the nucleus is spinning. That's the anti-parallel spin. So when the electron flips and you go from parallel to anti-parallel, a photon is emitted, and that photon has a frequency of 1,420 megahertz, or 21 centimeters in wavelength, and that's called the neutral hydrogen signal, or the H1 line. Okay, and it was predicted by a Dutch astronomer back in 1944, and the thought was, well, this should be detectable from areas in the sky where there's a concentration of hydrogen, basically. And the biggest concentration there is, it would be the Milky Way. So you would expect to see a strong signal from that. And it turns out that a few years after the prediction, Harold Ewan, and who's the graduate student who did the work, and Edward Purcell, his advisor, they built a large horn telescope. It's a big waveguide, and there you see it sticking out of the fourth floor of the Harvard physics building. I'm sure Buildings and Grounds must have loved that. And he detected on March 25th, 1951, he detected this H1 signal. That's considered one of the major milestones in the history of astronomy. And I like the picture on the left here, which is probably an early color picture, shows Harold Ewan at his electronics. Okay. So the hydrogen line then seemed like a good target. And of course, a lot of amateurs have been detecting that for a while. So what is my radio telescope going to consist of? Well, we make a block diagram. So we have our signal source, which is the Milky Way. Can you see the cursor moving around on the screen? Okay, so the signal is picked up by the antenna, which is actually composed of a dish and a thing called a feed. And then the signal is now an electronic, it's a current in a wire. It can go to a series of amplifiers, because you start out with a very, very tiny signal, microvolts or less, and you have to amplify it quite a bit. So it goes through a thing called a low noise amplifier, which both amplifies and filters the signal. You have a bandpass filter, fairly narrow for the H1 band. So that gets rid of it gets rid of a lot of the extraneous signals being noise. That could be both, well, that's primarily, I would say, artificial signals from terrestrial sources. So then we go through a couple more amplification stages. This basically here, the antenna and this thing in red, the low noise amplifier, they're all sitting on the antenna. Then we can have, once the signal is a little more amplified, we can have a cable bringing the signal, say, to a table, which holds a couple more amplifiers, and then another bandpass filter, and then it goes into the receiver, okay? And this is where sort of things have changed over the past, say, 15 years. Our receiver actually now consists of a software-defined radio dongle, which some of them are very small, look like a USB drive, and then a computer, which is running software. So that's the whole signal chain that's in the radio telescope. So now we can go through it bit by bit. The first part, which is sort of what everybody thinks of when you think of a radio telescope, is the big parabolic dish. Well, I chose a 1 meter dish because I live in Watertown and I figure I'm going to be transporting this thing around. So it's a 1 meter dish. It was built from a kit from a company in the Netherlands called ATMoB Design. It was actually quite a difficult kit because the components were quite raw. Anyway, so, and it's not solid, it's mesh covered. And that's an advantage because it really reduces the weight of the antenna. And it also, probably more importantly, it reduces the wind loading when the antenna is sitting on, say, a mount. You have to choose a mesh size that's compatible with the range of frequencies you want to study. And the mesh size I chose allows me to study frequencies up to about 10 gigahertz. Okay. But this is a reflector, just like the reflector in our telescope, and it's a parabola, so it reflects the RF energy to a focal point. Okay, and this is a very wide field lens system, rather, if you will. It's a f.45.
Wow.
Okay. And just to compare, when you're building one of these and you're pop riveting screening into this thing and cutting your hands, by the way, you take solace in the fact that the accuracy requirement is rule of thumb lambda over 20. And for a 21 centimeter wavelength, that's 1 centimeter. So what is the distance tolerance that you need for an optical mirror? Considerably smaller, right? So within the range of hand tools. Okay. So sitting at the focal point above the dish antenna is the feed, okay, which is actually the antenna. The dish is just a reflector. It's a passive part of the system. The feed itself, for such a high wavelength, is actually a fairly short stub of wire. It could be one wavelength long or half a wavelength long. So it's a few inches of wire or a circular piece of wire. There's another type of feed in which the wire is wound in a helix, and that's what I have. That came with the ATMoB design kit that I've purchased, and that's the feed in a protective container here. Often, radio telescopes will have the feed inside a horn, which, well, they often look like horns. They have a throat here and then a cone and the entrance point. And sitting in there is the little wire stud. That's the feed, okay? And the horn is a waveguide, and that further concentrates the RF energy. This doesn't have a horn. It's just got the helical feed, okay? So what's next is the low noise amplifier. So here's my feed, and you can see this black box sitting up here. That's the low noise amplifier from a company called Noelec. And it is designed actually, so there is enough business in the amateur radio astronomy area that a couple of companies actually build low noise amplifiers tuned to the H1 band. And this is one of the companies. So this has about 40 dB of radio frequency gain at 1420 megahertz. And here you can see the basic design. We have an RF amplifier, a bandpass filter, and another RF amplifier. So you take the signal, the raw signal, I would say, that comes out of your feed, and you immediately filter it and amplify it. So you never have a raw signal from a sensor. This is almost for any kind of device with a sensor. You never want to carry a raw signal through a cable, because you'll get tremendous losses through I²R losses, and you'll also get noise. So you always, at the feed or at the sensor in general, put your initial amplifier, or you can call it a preamp. And now we can have a coax cable coming off of the antenna. So, and we go on the table here. So here we're coming from the antenna, and we go into these two amplifiers. So they provide more gain. These are broadband amplifiers by a company with a very curious name called Utronics. So after more amplification, we have a final bandpass filter from a company called Mini Circuits. And then finally, the software-defined radio, which is this black chunky thing here, and the USB cable to the computer. So that completes sort of the amplification chain of the radio telescope. Okay, so now we go to sort of the heart of the matter, the software-defined radio. And what is that, and how do they work? And well, the first thing you want to know is, well, what is a radio? Okay, I mean, for those amateur radio operators out there, you could just log off or go to sleep. But in either case, here's on the left here is a block diagram of a super heterodyne AM receiver. And what we have is an antenna and a filter and an amplifier, and then a thing called a mixer, which mixes the RF signal with signal from a local oscillator. And the result of that mixing is you get a frequency, which is actually the difference between the two frequencies. And it's an intermediate frequency, which is substantially lower than the radio frequency coming in. And then you can further filter that. And then if this is a radio, you want to hear music, or if it's AM, talk radio, you send it through a demodulator, and then you can send it to an audio amplifier. Okay, so the antenna, so if we look here, here's frequency. And in this diagram here on the right, we have frequency, and this would be signal strength. We have a whole bunch of, let's say, radio stations. So this RF filter just filters these radio stations and filters out all the lower frequencies. Okay, so now we have this, it goes into the mixer, and the mixer essentially takes these stations and shifts them to a lower frequency. And then we have the intermediate frequency filter, which can then select out the radio station we want. Okay, so instead of radio station, you could say signal from outer space, like say the H1 line. So that's what basically a radio is doing. Okay, so the software-defined radio, the idealized software-defined radio wants to get, basically you want to get rid of as much hard electronics as possible. You want to do as much in software that allows you to vary the functions of the radio without having to build new electronic circuits. So the ultimate SDR, which you can't buy, would simply take the radio frequency, send it through a low noise amplifier, and then immediately send it to a block called an analog to digital converter. So what that does is convert the signal, which has amplitude varying with time, and it converts it into a series of numbers. So you can imagine in the analog to digital converter, a little man with a voltmeter, and he takes a voltage reading, writes it down on a piece of paper, waits a second, takes another voltage reading, writes it on a piece of paper. Well, writing on a piece of paper means storing in a computer memory. So after the signal goes through the analog to digital converter, you get a bunch of numbers. And once you have numbers, then you can mathematically process it. You do whatever you want with it, okay? The big problem with this ideal SDR is a little something called the sampling theorem. If I have a signal that's say 1.4 gigahertz, I have to sample that with my analog to digital converter at least as fast as 2.8 gigahertz. I have to sample it at least twice as fast as the highest frequency. And an analog to digital converter that can do that is expensive. Okay, so you're not going to get a low-cost SDR, ideal SDR, all right? So what do we do for real SDRs? Basically the kind of thing you can buy for 29 bucks on Amazon is you follow basically the super heterodyne radio architecture, okay? So our real SDR has an antenna that plugs in, and we have an analog front end, okay, which will have an amplifier, and it will convert to an intermediate frequency. Now that intermediate frequency, instead of being in the gigahertz, is in the low megahertz, okay? And now you send it through your analog to digital converter. And your analog to digital converter doesn't have to sample so fast, so it can be much cheaper. So that's why these SDRs can cost, $29.95 or whatever. You have further filtering and processing on the digital side, and then ultimately information, this numbers, a stream of numbers comes out through the USB port to the computer for processing, okay? And what kind of processing can you do? Well, you can filter, you can demodulate it, you can do foray analysis, do whatever you want, all right? So here is the software-defined radio used in my telescope. It's a bit of it's the preferred one right now for the amateurs. It's a bit more expensive. It's about 130 bucks as opposed to $29.95. It has a range of 24 megahertz to 1.7 gigahertz, and it has a 12-bit ADD converter, which means it can divide the range of amplitudes into 4,096 steps. And this is important, it can do 10 megasamples per second. Okay, so you can sample fairly high frequencies. Okay. And here is my complete system sitting in my backyard at my Watertown dark sky site. Okay, and you can see the antenna here, the 1 meter dish is right, I'm running the cursor around it. This sort of flouncy screen around it is to prevent noise from the ground from hitting the feed, or if the feed is not properly aligned, it might be pointed a bit over the edge. And the ground is a huge source of thermal noise. So this is basically to shield the antenna from thermal noise, especially since I'm just sitting on the ground. I don't have a tower. And you can see the low noise amplifier up here. And then these little boxes here are my amplifiers and the software-defined radio, and there's my laptop computer. And we're ready to roll, just about. So let's talk about now the software and the processing that we're going to do to these signals, okay? But before that, we have to go through a little preliminaries, okay? So we start with Jean-Baptiste Fourier, who developed a theory that you can take a signal and you can decompose it into a series of cosine waves. And those series of cosine waves have different amplitudes, but their frequencies are all harmonically related, meaning they're all integer multiples of each other, meaning one is at frequency X, the other is at frequency 2X, 3X, 4X, etc. So here's an example. Here's kind of a strange looking waveform, but this shows how we can either construct it or deconstruct it. So I can start out with a DC waveform, this up here, just a straight line, okay? So you can call that no frequency. And then I'm gonna add it to this waveform here, okay? And when I add the two, what I'm doing basically is shifting this signal up. So you might say I'm giving this a DC offset, but I'm combining two waveforms. So now I have this signal, and now let me get out this somewhat higher frequency. Well, it's a frequency twice of what this waveform was. And let me add that to this compound wave. And now I get kind of this up and down structure here. And then finally, here's a lower amplitude waveform, but it has 6 times, rather 3 times the frequency of this original one. And let me add it to this. And now I have created or synthesized this new waveform, And similarly, I can take this waveform and take it apart and look at this component, that component, that component, that component. More importantly, I can look at the magnitude or the power of each of those components. Okay. And this slide I threw in because the new president of our club is a mechanical engineer, and this is a great mechanical analog to the Fourier series. So what we have here is a series of rotating disks. You can look at each rotating disk as a waveform of a different frequency, its rate of rotation, and the diameter is the amplitude. And basically, imagine you have a pen stuck on the smallest disk, and you're sliding paper underneath it, okay? And you're tracing out a waveform. So you can see in this one that says square wave, we're using sinusoids. Rotating disks just generate sinusoids, but we're creating a square wave. I mean, it's not perfect. You'd need a lot more circles for that, but it's kind of neat. This would definitely be something that you could do with a 3D printer. And here on the right, we're doing the same thing, but generating a sawtooth wave. So we know that a waveform can be broken up into a series of sinusoids, okay? So we can now take our signal that's gone through amplification and filtering, and we could perform a Fourier analysis on that using a mathematical thing called the Fourier transform. And what that does is give us, so that the Fourier analysis will split up that waveform into all these frequency components, and the Fourier transform will give you the magnitude of those components, okay? And when I present that in a graph, now instead of showing magnitude versus time, that's a time domain expression of a signal. That's what you'd see in an oscilloscope, for example. Now I can show you frequency versus the amplitude of each component. That's the spectrum, okay? That's called the frequency domain expression of a signal, hence the title of my talk. And that's pretty much the way radio astronomical data is presented. So here's just a final slide. Let's take a signal source. This isn't the galaxy, this is a kalimba. And we're playing two notes on the kalimba, A and E, and this is the time, the upper graph is the time domain signal. So this is time and f of x, just call it amplitude. And you can see this complicated waveform. But now if I do a Fourier transform and plot the results, I have amplitude here and frequency. You can see I get two peaks, one at 440, which is the note A, and one at 659 hertz, which is the note E. Plus I get some other frequency components in there as well. That could be for the special sound or ambiance of the kalimba. But I didn't build this disc antenna to listen to kalimbas, okay? I want to make a radio telescope. Okay, so we have to take this signal and do some signal processing, okay? And what are the things we have to do? So once I've got my software-defined radio streaming in those numbers, okay, now the software that's running on the computer can do all this processing, okay? And what is that processing? Well, there's a lot of background noise that can be removed. And then you do the Fourier analysis, meaning you separate the incoming signal into individual components. You measure the power of each wave. And then you integrate to further remove noise. And then also you have to remove the instrument bias from the spectrum. So here is a spectrum. So the vertical axis would be magnitude, the horizontal axis would be frequency. And here you have the frequency response of an amplifier within this chain. And you can see, ideally, if you give an amplifier noise, you want to see a straight flat line. So in other words, that amplifier should be like, have the same response at all the frequencies in the range you're interested in. But that's not the case. This amplifier is more sensitive here, less sensitive here, more sensitive here. So you get this thing. So part of the software removes this instrument bias. Okay, so the object of interest is not riding up and down hills. Okay, so the software I'm using is a package called SDR Sharp. It runs on Windows machines. And this is an example of the output of SDR Sharp just as it comes. And what you see up top is the power spectrum of a signal. Okay, so vertical is amplitude and horizontal is frequency. And this structure right here, you see sort of this TP surrounded by two boxes. That is a powerful FM radio station. It's also a high def radio station, and these side lobes are carrying information that the high def needs. Okay, so lower power or maybe radio stations without such a big budget would have just sort of a single sort of lump or peak. And then below this spectrum in this sort of graphical form, you have what they call the waterfall way of displaying. It's the same kind of a display, only here amplitude is represented as color, sort of the hotter colors being higher amplitude. Okay. Again, the cross axis here is frequency, but now the long axis streaming down is time. So this is sort of like the chart recorder output. So this thing is coming down. So anyway, these things are, it's lots of fun to get one of these cheap SDRs and download SDR Sharp and just search around and listen for radio stations and all kinds of stuff. By the way, they're blocked for cell phones, so you can't go listening into people's conversations. Okay, so to run the radio telescope, you don't just use SDR Sharp. Some amateur wrote an addition, they call them plugins, to the program, and this is called the IF averaging plugin. Okay, so here you end up with using SDR Sharp, you get an IF average window, and here is magnitude in decibels. Notice that's negative, going way, way down. So this is showing we're looking at very, very low, very, very tiny signals. Okay, and this is frequency. There's 1420.4 megahertz right there. For software-defined radios, you're going to see generally a big spike in your graphs, and which is an artifact of the software-defined radio. Okay, so this is what we're getting out of our SDR Sharp with the plugin. Okay, and that's what we want. Okay, so to show you my results, okay, and again, I didn't make up this way of displaying it. I'm copying what other amateurs have done. Is you display this window, which has your signal, and then you size a window with stellarium, enhance the galaxy. If it's during the day, press the A key to turn off the sun. So, and then you record screenshots at regular intervals. You can use a little program called Chronolapse to do that. Okay, so I set this up. And I said, okay, we're going to record screenshots every 5 minutes. I'm going to let this run for 12 hours. And my radio observatory, my telescope is mounted, I would say, in a micro Arecibo fashion. In other words, I'm sticking it in a pail, having it pointed up. Okay. The next step, of course, is to put it on a movable mount. But this is enough to see what we can get. So what you're doing is you're pointing it at zenith. Of course, that's not the North Pole, so things don't rotate around zenith. So the Milky Way will swing past zenith a couple of times in the course of the day. Okay, so I'm going to do a 12-hour zenith scan. All right, and so I will just sort of rapidly tap through these slides, and you look here at this fuzzy business, that's the Milky Way. Here is zenith, that's where my telescope is pointed, okay? So I just tap along, and I don't know if can you see this, it's dark. There is a timestamp here, okay? Unfortunately, it's hard to see, but let's just tap our way through, and you can see now the galaxy is approaching zenith. And uh-oh, what's happening here? I'm starting to get, well, actually at this point, it sort of looks just like my legs, which are full of mosquito bites, but this isn't a mosquito bite. This is actually the H1 line. which is spread out because it's traveling through quite a bit of the universe and going through clouds of electrons and things that will cause it to spread out. It also is Doppler shifted. So you can see now zenith is crossing, or rather the galaxy is crossing zenith, and I'm getting a strong H1 line here. And as the galaxy moves away, unlike my mosquito bites, the H1 line diminishes. Okay. So we keep going, and it's kind of hard to see because even though I turned off the sun is coming, and I don't know, it's extra bright here. But we are re-entering an arm of the galaxy right around here, which means we're getting another bump. And then, and I think this is because the sun starts to overwhelm, and it's a huge, source of neutral hydrogen signal. The entire plot drops, okay? But at this point, we've passed the galaxy, so we're not seeing the tight neutral hydrogen. So that's my result, okay? It may not look like much, but to me, it's as beautiful as the pictures we saw on Tuesday from the Webb telescope, okay? So next steps for me, actually I did another zenith scan last night, and of course it was pouring rain, everything was covered in plastic, but I let it go. I did a 17-hour scan, and I got some bizarre results, and I think it had to do with all the water that was on the antenna. I have to discuss this online with some of my newfound radio astronomy friends. But anyway, what I'd like to do is get signals of sufficient quality that I can look at the Doppler shift, okay? Because at some point, you're looking at an part of the galaxy that's coming towards you, in which case you would have a blue shifted signal, or if you're looking at a part of the galaxy that the Milky Way that's going away from you, you would see a red shifted signal. And what you can do with these measurements of the Doppler is calculate the rotational velocity of the Milky Way, which I think is a pretty cool thing to do. And then beyond that, I've got to get this telescope on a tracking mount, whether it's an equatorial mount or a motorized azimuth mount, regardless. I want to be able to move it around so I'm not just stuck to zenith, and I can try and do some radio source mapping. So that's basically what I've done over the past few months. There's plenty of sources of information, of course, online. Two big ones, if you're interested in the neutral hydrogen line, the two big ones to go to, well, the big one to go to in general is SARA, Society of Amateur Radio Astronomers. It's only $20 a year to join. They have a phenomenal Google group with people that just get right back to you and are very, very interested in what you're doing. And of course, this covers all aspects of amateur radio astronomy, not just telescopes with the H1 line. There's a group out of West Virginia University that had a funded educational program called Digital Signal Processing in Radio Astronomy. And they had this Horn telescope project. So basically they reproduced Ewan and Purcell's Horn telescope for measuring the H1 line. And they have complete, actually it was an REU program where they would invite teachers to learn how to construct these things. So this is an intriguing device that looks fairly simple to build. Maybe a few of you in the club maybe we could do this as a club project. Anyway, these two sites have tons of information on observing the H1 line and analyzing data. What started it all for me was this website called Cheap and Easy Hydrogen Line Radio Astronomy with an RTL SDR, blah, 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 blah. So this basically had some guy used a repurposed satellite dish antenna, and he actually had that way of displaying the data where you have the IF window and chronolapse. And he had such beautiful pictures, and it literally took me months before I could even see the signal, and it was quite frustrating. I realized one thing. The fellow lives in New Zealand, and I think the center of the galaxy is much higher in the sky in the southern hemisphere, which is the biggest source of the H1 line. So he had a much brighter source he was dealing with. Anyway, but lots of good information there. If you're interested in other phenomena, well, there's Radio Jove, and that's looking at in the ham bands, I think 20 megahertz, looking at Jupiter signals. And then there's the Super SID project. These are all educational programs. This is out of Stanford, which looks at ionospheric signals caused by the sun, basically space weather station. For understanding software-defined radio, if you're into MATLAB, they have a toolbox for software-defined radio, so you can write programs. They also have a free ebook, which is an excellent textbook on software-defined radio. And finally, for you Linux buffs, there is the GNU radio tools, which again allow you to build software for, say, a radio telescope. And one advantage of using the GNU tools is you can then put your program on something like a Raspberry Pi and have your telescope just be completely remote. So that is my talk. Okay, I leave you with this picture. If you walk up the hill from the clubhouse to the big haystack dome, you'll see this off to the side, this lonely little, I think it's a 2-meter dish. And this was part of the small radio telescope program at Haystack. I don't know if it exists anymore, but it wasn't a cheap radio telescope. It was sort of a low-cost radio telescope for schools, say, to build. But this thing is just sitting there. And as far as I could tell, it's not attached to anything. So I was thinking maybe if we could reach out to Haystack and say, hey, is this thing operational? If not, would you mind if we made it operational, say, and made it remotely operational and then put it on our website and made an educational thing that Haystack could also access as well. So it may be a way to have access to a very nice radio telescope. So that's my talk. And are there any questions? What do I have to do, Corey? Do I have to?
That's all. I think if you want to stop sharing, there's a red icon at the top.
Okay.
That's really, really
Yeah,
cool.
there.
I've always been interested in radio astronomy.
Okay.
I've seen some other projects that involve SDRs, and those have piqued my interest as well. So this is like a perfect synthesis of tentative interests.
It's really cool.
Yes. Especially if you're a ham radio operator. I'd say if you're a ham, you're perfectly trained for this.
Yep.
Especially the antenna aspect.
Yep.
Yeah,
Question. Oh,
like there's
Christine, you have a question?
Yeah, thanks, Tom. That was fun. What was the very spiky, strong, narrow signal at 1420 megahertz?
From what I've read, it's an artifact of the software-defined radio. Although it does vary in size. And last night when I had my drenched drift scan, at one point that spike disappeared. So I'm going to have to discuss with other amateurs what the effect of water on the antenna does to the signal. It definitely makes the baseline really tilt, but we'll call it an artifact. It's not ET.
It's because of the fact that you're doing downshifting of the frequency by mixing with with an intermediate, with a local oscillator to get an intermediate frequency, and you're only having a 5 megahertz bandwidth because you have a 10 megahertz sampling rate. That's what it is. So you're looking at the oscillator.
Oh, I see. Michael Toops.
Yes. What type of noise figure are you achieving with your LNA?
What type of what?
Noise figure or sensitivity you're getting with the LNA?
I don't know. I don't, I haven't quantified that. You can look it up. I mean, I have the website, on all these slides, so you can look it up in the company, but I can't tell you off the top of my head. Sorry.
All right, thanks.
Just trying to go back to that.
I know where there's a one of the old fiberglass satellite dishes. If you ever get the urge for a bigger dish.
Oh, really?
Yep.
Where is that?
My neighbor has it stuck in the woods.
Huh. How big is it?
It's probably 4 meters.
Oh my God.
You need some counterweights for that mount.
Yeah.
Yeah.
It's fiberglass.
Yes.
So is it coated? Does it have a metallic coating?
It must, or it must have.
Yeah, it must have.
That'd be pretty awesome.
But
Yeah,
he's a ham radio guy. He would be thrilled to give it to somebody that wants it.
For the mount, if you need something custom for because it's kind of an awkward shape to holster and move and counterweight, there's a great project called OnStep where you can use like the guts of a 3D printer and drive the stepper motors, so you can come up with like a single arm Dob mount or something, and then just belt some stepper motors in, and all the driver software is taken care of. You just configure.
OnStep.
OnStep, one word.
Yep.
But if that's interesting to you, I've been using it for a while, and we could collaborate on it.
Yeah, that might be. I mean, right now I have an IEQ 4045 equatorial mount, and contemplating bolting that to a dovetail plate just to see what I can do. But it is, I mean, it's not heavy. It's as you could say, it's very awkward.
Yeah.
But any other questions? Philip.
Oh yeah. So with that masterpiece, whatever I call it, how far have you been able to hear through the noises? Did you get that far of being able to like hear in like a space of like what the sun sounds like, or like what certain galaxies or like situations of like if there's like a comet coming? Did you get like that far in space to hear?
As far as hearing is concerned, if the signal is extremely small, so if you look at the non-averaging window, the standard window of SDR sharp, you will not see anything. You'll see just little ripples, okay, and nothing distinguished. It's only after you do all this averaging that you actually see some sort of signal. So I don't know if we can, turn that into something that a tone or something like that. And I definitely don't have the angular resolution to point this thing at a variety of little meaning an angular sized galaxy. So I can't do a comparative study at this point.
I know you said something about like whatever the phrase about like you said you were talking about a radio station, then you said like it's like the noise of like space. Like I didn't know what you meant by that. I wasn't sure if you meant like whether if you can hear like noises of what planets sound like if you got that far. I didn't know what you meant by that phrase.
Oh, I probably misspoke. But the radio Jove, which looks at, I'm thinking 20 megahertz. Jupiter is very noisy in the RF, and that would be something I would be very interested also in working on. What Radio Jove uses instead of a dish, because they're looking at 15-meter wavelength. It's quite a feed in the dish. They use dipoles. Actually, they use 2 dipole antennas connected in a they're phased. So it's a phased array. You can steer it electronically. So it's a bit of a chore to set up those antennas, not because they're heavy or anything, they're just lengths of wire, but they have to be on the order of 20 feet high and 2 of them next to each other. So definitely beyond my backyard.
Okay.
Hey, Philip, just to clarify, when people using radio or electronics talk about noise, they're not talking about stuff you hear, they're talking about stuff they don't want in the signal. It's stuff which is not what they're looking for. So it's like if you think about it as when somebody is trying to listen to something they really want to hear, and there's a lot of noisy chatter that they don't want to hear. It's kind of like that, which is why they call it noise. It's stuff that you don't want.
I know they didn't want to hear people talk and stuff like that. I got to that part. I thought they were trying to like hear like something as something else, like something related to the project.
Yeah, it's just they call anything that they don't want. They call noise.
But also it's never converted to sound.
Right. Yeah. There's no point really. Is Doug saying something?
Trying to, yeah. If you did convert it to sound, it would basically sound like white noise.
Right.
Your signal is white noise against the background, which is ideally white noise. So you're just hunting for more. Also, rain on antennas creates noise. So that's probably what happened to you. Rain particles, rain droplets are charged. So the charged objects hitting your antenna creates noise.
Great. Thanks.
Oh.
There are no other questions. I think I'll officially close the meeting and then keep it open and hang out.
I don't want to call it a question, but it is interesting to like learn that Jupiter can be noisy, like the radio Joe, if that's the right term, if that's the right phrase, yeah.
Well, I mean, noisy meaning emits signals. Okay, I mean, noise is being used in two contexts here. One is that the technical definition is noise is your unwanted signal, and there's thermal noise and there's noise by unwanted signal sources. But then the other thing is I'm making noise,
I meant to say signals from Jupiter. That's probably what I meant to say for the signals. Excuse me. Yeah.
Yeah. Okay.
I've heard signals from Jupiter. They basically just sound like white noise.
Oh, like the television, like the old box.
Well, and a little like an FM radio when it's tuned away from any station.
I see. Yeah.
So with that, I think I'll officially end the meeting.
Okay.
Our next meeting will be September 8th, 2022.